Okay, hi everyone. Welcome to the exercise class. I'll just slowly start. So today we're going to discuss two topics. The first one concerns the dynamics of an ideal clock, and the second one concerns the limits of the Hamiltonian of the quasi-ideal clock. So the idealized clock, we already discussed it in the lecture. We can model it by assuming that the time operator is the position operator of the clock, and the Hamiltonian in this case is just the momentum of the clock. And crucially, this idealized clock has three properties, which we're going to show now. So first, it has a distinguishable basis of time states. Which of course something we would like to have if we want to label something as a clock. So the time stays here, of course, we take it into a parenthesis because this is not actually the time operator that we are considering. We're just taking the position operator of the system acting as time. But in any case, it does have this distinguishable basis of these states, x. Distinguishable in a sense that if you take the scalar product of two, or overlap of two states of this basis, x and x prime, they give you the delta function. So they are zero for all states for which x is not equal to x prime. And also, we can notice that since we take the Hamiltonian to be the position operator, then the evolution of the state, which is given by the operator e to the power minus ith, acting on the state x. So this would be essentially this. And this operator, due to the having this momentum operator in the exponential, it acts as a translation. So from state x, we arrive to the state x plus d, because this is how we would usually write the translation operator, spatial translation operator, which moves the state x to the state x plus d. So in this sense, if we were taking time operator as the position operator, we see that the time translation, in our usual sense, corresponds to the spatial translation. Which means that when we evolve the system in time with our Hamiltonian, the natural evolution passes through all the states x prime, such that x prime bigger than x. So during the evolution, passes through all x prime bigger than x. So in that sense, yeah, x, like in the sense of a time operator, it moves forward. Okay, so this is the first property which we would like the clock to have, and which it has. The second property is the so-called continuity property. And this property is guaranteed already by the fact that we just shown that the time translation is equivalent to the spatial translation for this clock, for all states of the clock. So for example, if we write for an arbitrary state of the clock, psi this translation, it of course will just give us this. And this also holds for arbitrary small t. So what continuity means in this sense is that we can translate for at as small kind of times as possible. So in a sense, time flows continuously. Okay.
Excuse me, I have a question.
Yes.
I don't see exactly how this property is any different from the one we've established before, because if we are already defining that this operator on x gives x plus t, then what you're writing for me just seems like a logical conclusion.
Yeah, it is a logical conclusion from the first. I mean, it's not necessarily it does not necessarily follow from the fact that we just have a distinguishable basis of time states. Like, we can imagine that we can have a basis of time states, but which, for example, would have like smaller measure than this basis, which would also be distinguishable. However, it wouldn't it wouldn't ensure the continuity.
Okay, so it's something different, right? Like translation doesn't.
So, for example, you can have a distinguishable basis of time states, which would be like x plus delta x plus 2 delta x, and so on. And they will also be distinguishable because like they would only so the overlap between these states would be 0.
Okay.
But it doesn't it doesn't give you the continuity. It gives you this kind of coarse-grained continuity where you're only able to move by this delta x.
Okay.
But I mean, what I'm saying in the second part kind of follows from the from this intuition I already gave in the first part. It's just like I'm establishing that kind of this basis has to be of this time states has also be kind of continuous.
Okay. Okay. Thank you.
You're welcome. Okay, and the third property that we would like the clock to have is that it should allow for a perfect continuous autonomous control on some external system. So let me explain what I mean. So what I mean is that, like, for example, if we add a position-dependent potential to the clock, then it should remain continuous. So in this sense, we can see the ability of the clock controlling the external system as adding this position-dependent potential. And what we would like to have that is, even if we add this position-dependent potential, the clock still remains continuous, so it doesn't become like more coarse-grained. And this is just to show this. We just need to kind of add this potential, which we say it's potential V, and then see how the evolution the clock changes after time t. So what we would like to have is that this equals some phase, some accumulated phase to the potential, and kind of the same translated state of the clock. And indeed, this is actually equal to the following. So the first term just gives us the phase, and the second term is just a shifted state of the clock. So let me prove this. So to prove this, let us denote psi of xt as the component of the wave function at time t and position x. So basically this. Then what we would like to, and then subsequently this term is just psi of x minus t0. And then essentially what we need to prove then is that psi of xt equals e to the power minus I, this integral psi of x minus t0. Okay, so to do so, we need to just verify that it is a solution to a Schrodinger equation for the clock. So need to verify that it's a solution for Schrodinger equation for the clock. So let us write the Schrodinger equation. Here we assume that h bar equals 1. So what we get then is I derivative with respect to t psi of xt equals, so first we write the Hamiltonian of the clock, which is minus I derivative with respect to x psi of xt. So this is just the action of the momentum operator, and then the potential. Okay. Then let us just insert, instead of the psi of xt, our the thing that we want to show is equal to. So this phase by psi x minus t0. And then just make sure that indeed this equality holds. Okay, so the first part is we're going to take the derivative with respect to t of psi of x of t. So this is taking the derivative with respect to t of the following. I'm deeply sorry. There is a wasp which keeps annoying me. Yeah, no, it's good. So here we have this part. Then we take the derivative by parts. So first we take the derivative of, this part, and here we can note that the following holds. So d derivative with respect to t of psi x minus t0 is equal to minus derivative with respect to x psi of x minus t0. And so this allows us to write the first part as a minus derivative with respect to x psi x minus t0 by our phase. So this was the first term. Then the second term, we take the derivative of our exponential. So psi of x minus t0 is left behind, and the derivative of this exponential is taken, we can take it using the Leibniz rule for like such integrals. And what we're gonna get is this by minus I v of x minus t. So let me remind you the Leibniz rule, because personally I forgot exactly how it looks like when I was solving the exercise. So just as a reminder, so I'll just say that this is due to Leibniz integral rule, and the Leibniz integral rule is the following. Oh yeah, so this is just a reminder. When we have an integral, when we're taking a derivative with respect to the boundaries of the integral, then we can use the following formula. So this formula is of course more general than the case we're applying it to, but yeah, I think it's useful. So we just take the function f at the upper boundary and then take the derivative of this upper boundary. Then we subtract the function at the lower boundary with the derivative of the lower boundary. And then we also add just the derivative of the function in the integral, if of course it depends on this parameter, which in our case actually doesn't, but again, this is just a reminder. Okay, and so this was the rule that we used to take a derivative of the exponential on the previous page. And hence, just to rewrite what we got that the time derivative is equal to the following. This by our exponential, I'm not going to write it through because it doesn't change, and minus I v of x minus t, and there we had psi of xt, which psi of x minus t 0, and again by the exponential, and this is actually just psi of xt in a way we defined it. So we can rewrite this as minus this exponential minus I v of x minus t psi of xt. Okay, so another term in the expression was the derivative with respect to x. And here we do essentially the same. So we again write it out in terms of psi x minus t0 and our exponential. And then we take it by parts. And we again need to use the Leibniz rule. And what we get in the end is the following. So this is just the first term is just the derivative of the first part of the expression multiplied by the exponential minus the derivative of the exponential now with respect to x. So here we get this. Okay, and then we see that we see the following, that we needed to show that this equation holds. I would even copied my so we just substitute instead of derivative with respect to t this equation. and derivative with respect to x. Oh, sorry, maybe I just. Respect to x here. And we see that we get exactly what we need because this term goes away with this term goes away with this term, and we're left with exactly term v of x psi xt, which is here. Okay, so then we prove that psi of xt satisfies Schrodinger equation, which means that our initial guess about kind of adding this position dependent potential does not alter the continuity of the clock. So it kind of goes out of the expression in terms of the phase. So this guess is correct. Okay. So now let us take a step back from the ideal clock and just to see how it can be useful. And before we consider a setting with the system and the clock, let us just consider a setting with the system. So suppose that we have a system S, and then we want to implement some energy preserving unitary. So we have a system S at the state rho S, and we want to implement some unitary US. And we want to implement it from time ti to the time tf. Okay. And to implement this unitary, we can just kind of reduce it then to some term in our Hamiltonian, which would like practically correspond to implementing this unitary. So we need to some time-dependent interaction term. So for this, we first find a Hamiltonian which corresponds to this unitary US, which we call the interaction Hamiltonian. Yeah, and this is possible because for every unitary operator, we can always find such a self-adjoint operator. And then we can write the pseudo-Hamiltonian as the following. So it's the Hamiltonian of the system plus the interaction Hamiltonian by some function which depends on time, v of t. And v of t is such that it only has support on the ti-tf interval, and it's also normalized. So if we integrate v of t from ti to tf, we get 1. So essentially, this is our way of saying that this interaction only is only going to be implemented from the time ti to the time tf, because this is how, because we only want to implement our unitary in this time interval. Yeah, and this is called a normalized pulse. Okay, then the state of the system rho s after time t is of course just expressed as the action of the Hamiltonian for time t. And one can show this, and I'll just leave it to you, that this actually can be rewritten as, so first we just act with the Hamiltonian of the system, and the action of the interaction Hamiltonian is written as the integral from ti to t, where we integrate the pulse during that time until time t. And here is rho s of 0, or better, I think, to write that this is rho s of ti. So the initial time. And on this side, we would have the same, but Hermitian conjugate. Okay. Yeah, and we can actually separate this h. So we can actually separate the exponential of h as the multiplication of exponential of the terms xs and xs interaction, because we assume that the unitary is energy preserving. And since the unitary is energy preserving, these two terms commute, and then kind of separating the exponential into the product of two exponentials is allowed. Otherwise, of course, for other unitary interaction, this wouldn't be that easy. Okay, and since we have this property of these two Hamiltonians commuting because of the fact that I just mentioned, it means that they have a basis, a common basis, in which they're both diagonal. So then we can write xs as in its diagonal form in this basis as following. And we can also write the interaction Hamiltonian as diagonal in the same basis. And we just label their diagonal elements as ej and omega j. And then the free evolution given just by the Hamiltonian hs, we can always write it. We just write the elements of the density matrix here. So this is nothing new. But if we label our elements of the density matrix as this rho mn, then for the interaction, we can actually rewrite the state of the system S after time t as following. And here we have. So we see that here, just each element of this matrix gains the additional phase, which is given by the by this pulse potential. And also, of course, depends on which what are the diagonals, the corresponding diagonal elements in the decomposition of the interaction term. Okay, so this was just like to see how we can model this time-wise interaction for one single system. But now what we would like to have is, like, you could ask why did we bother even with the idealized clock before? But now the idea is that we want to remove the explicit time dependence from this model, and instead of that, we just insert a clock and replace this background time, this time interval from ti to tf, with some with this time parameter given by the clock, which, as we saw in the idealized clock, is actually the position of the clock. So now the idea is to replace the background time with time degree of, rewrite it, an idealized clock. So that means that we need to add one more system. And then the total Hamiltonian becomes, so we have our initial system Hamiltonian, plus we have the Hamiltonian of the clock. So this is just, as we saw, it's PC, right? It's momentum. Plus we have our interaction term, but then we couple it on the side of the clock to the potential V, depending on the time degree of the clock, which is the position of the clock. Yeah, and I claim that this implements the unitary US, which we were considering on the previous page. So to verify this, you should just start with the initial state of the clock and the system as a separable state with only one term, and the clock starting in some pure state psi. And also the hint would be to write the later state in phi j basis. And then you'll see that actually by coupling to the clock system with this in this manner, so instead of having our joint, so instead of adding the interaction term to the Hamiltonian of the system multiplied by this pulse, we just express this adding this pulse as just adding a clock system with the same time degree. So kind of the usual product here just converses to the tensor product with the clock system, which describes the same normalized time pulse, but just in its own time coordinates. Okay, so this is like the last part. I'll leave you to you to verify. You just have to evolve the state and then see what is the final state of the system as. Okay, and in the remaining time, I'll talk a bit about the quasi-ideal clock, and we'll take a look at the, at least quantitatively, to the limit of the quasi-ideal clock. So the quasi-ideal clock is, as it goes from the name, it's quasi-ideal idea of the implementation of the idealized clock. And the quasi-ideal clock is usually seen as a system, a d-dimensional system with equally spaced energy levels. So the Hamiltonian of the quasi-ideal clock is just the following. So this is essentially this equally spaced energy levels. Two levels are separated by energy omega. So omega, in this sense, so in the lecture, Ralph already discussed like what are these states, what is the basis of this Hamiltonian, what are the time states, and what are the actual time states that you use for the clock. And so the states of the clock. What is important to understand about this Hamiltonian is that omega determines two things. So it determines first something that is called the recurrence time of the clock. So what is the recurrence time? It's the time after which the state of the clock comes back to its initial state. So T0 is actually 2 pi over omega. And why? Because if we look at the evolution operator, e to the power minus I h clock evolving for the time T0, then this will give us e to the power minus I some and omega 2 pi over omega en. This gives us e to the power minus 2 pi I n. Minus 2 pi I some n en. And this gives us the diagonal matrix with all diagonal entries equaling 1. So this is just the identity operator. And this means that if we evolve the system for time T0, it just comes back to its initial state. So that's why it's a recurrence time. And the second thing that omega determines, which I already mentioned, is the energy spacing. So for example, if we just naively think about taking omega to 0, this would correspond to kind of having this energetically bounded but continuous set of energy levels. Okay, another thing that I like to mention is what is the basis of the time states of such clock. So we usually label them as theta k, and they're written as following. Nk over d en. So coming from so the idea of this time states is that, for example, they rotate into each other after some time T0 over d. So if we evolve the state theta k for the time T0 over d, we would actually get the next state. So this also kind of coincides with our understanding of the clock that, like, if we look at the clock, if we look at our usual clock hanging on the wall, then we see that like we have this so the arrow is pointing towards, I don't know, 1, 2, 3, 4, 5, and these are exactly this states theta k plus 1, theta k plus 2, and they're time-wise equally spaced. So rotate into each other after delta t equaling T0 over d. Okay, and if we start looking at the limits of this clock, then what we get is the following. So for example, if we look at the limit of d going to infinity, so the number of this energy levels going to infinity, and also given that 2 pi over d omega has to go to 0, so we can imagine kind of situation where d goes to infinity, but 2 pi over d omega does not go to 0 due to the omega, I don't know, overpowering d somehow. But let us just consider the case when it's an infinite dimensional clock, but it also satisfies that 2 pi over d omega goes to 0. And what is exactly 2 pi over d omega? 2 pi over d omega is equal to this delta t. So the spacing between two time states. So from the fact that d goes to infinity, we can conclude that we will have still discrete energy levels, because omega does not go to 0, does not necessarily go to 0. So we're going to have oscillatory behavior, because we still have our kind of harmonic oscillator situation. But from the fact that delta t goes to 0, we actually get a continuous time states. The other situation is when d goes to infinity, omega goes to 0, but omega d stays constant. This situation means that we will have continuous energy spectrum, because omega goes to 0 and the spacing between levels essentially goes to 0. So we will not have discrete levels anymore. But because omega d is constant, this means that delta t, kind of the time spacing between two time states, is going to be some constant. So it's not going to go to 0, which means that we will get discrete time states. Unless, of course, omega d unless, of course, we also have omega going to 0, delta t going to 0, and d going to infinity. In this case, we'll just come back to our usual continuous limit of the Hamiltonian being the momentum of the clock. Okay, so just to recap, so first we were looking at the dynamics of the idealized clock with a Hamiltonian, which is a momentum, essentially, which takes time as a position of the clock. And there we saw like three crucial properties of such a system, which are that we need to have a distinguishable set of basis of time states. We also need this clock to be continuous, and we also need like this perfect control, in the sense that if we add the potential depending on time, which is in this sense position, then the continuity of the clock is not disturbed. And then we saw how to, using this clock, implement time-dependent kind of Hamiltonian, or implement a unitary in the particular time interval. And for the quasi-ideal clock, we looked at the a Hamiltonian, and then quantitatively kind of argued what this Hamiltonian corresponds to, what the behavior of this clock corresponds to for different limiting cases of the dimension and the spacing between levels. Okay, I think this is all I wanted to say today. Are there any questions? So concerning, maybe one more comment I add is concerning the clocks. There is quite a comprehensive paper which I also used to prepare for this for the exercise class, which is written by Ralph, Misha Woods, another postdoc in our group, and Jonathan Oppenheim, which kind of goes through this whole derivation for, especially for the quasi-ideal clocks, and talks about their dynamics and control and limitations. So I would, and it's in open access on arXiv, so I would recommend you to check it out if you want to understand this topic deeper, or you're not clear with some derivations in the course.